Today we are working on learning how to find the area and circumference of circles. But instead of finding the area of an entire circle, we're only going to find a small wedge of the circle, which is called area of a sector. And then instead of finding the circumference all the way around the circle, we're only going to find the circumference is called arc length. And that means that we're going to find a piece of the circle part on the edge, like the crust on a piece of pie. And so when you think about the area of a sector, you're looking at, well, I guess we should say, how much pie can I eat? If you think of a circle as when you color it in sections, and so this section is a fairly large piece of pie. Somebody's eating about a third of this pie in one piece, and so if you think of it like that, then you can see how it works in terms of a sector. So let's talk about just regular area. When you find regular area, you have pi r squared, and this is for the entire whole circle. But in our problems, we're only going to want part of a circle, a fractional part. Now, you heard me say that I thought this looked like a third of the pie. Why is that a third of the pie? Well, when you want to do part of a circle, you take how many degrees it is out of 360, because 360 is a whole circle, and multiply it times pi r squared, and that will give you the formula for area of a sector, because it's the area formula times what fractional part of the area do you want. So like in this example, I would have 120 degrees over 360 degrees times pi times 6 centimeters quantity squared. Now, as we work through the question, there are many things you can do, and for right now, we're trying to get exact answers. So we're not going to multiply the pi into it. We're going to give you our answer in terms of pi. And then later, when we do some word problems with this, we'll work on getting decimal answers. So first, you can cancel out the degree marks, because those units cancel. And you can reduce this fraction zeros, because a zero on top and bottom will cancel. Then you can see that 12 over 36 reduces to 1/3. And that's where I was talking about. I thought this looked like about a third of this piece of pie. And then we can multiply that times pi. And then we have over here, we want to do 6 centimeters squared. So 6 squared is 36, and centimeters squared is centimeters squared. Then last but not least, you multiply your numbers together. What is 1/3 times 36? Well, really, that just means 3 divided into 36. 3 goes into 36 12 times. So I have 12 pi as my answer. Now, I could multiply that together and get a decimal. It'd probably come out to be more than 36, because pi is already 3. But the key here is, I'm just trying to give an exact answer right now. So I'm going to leave that 12 pi centimeters squared. Now, why it's so important for you to put the units in this problem is because 12 pi looks like an angle, but in this case, it's not an angle. It's just I haven't multiplied it out to get the final answer to a decimal. And so, if without those centimeters squared, I would think this was in radians, because 12 pi looks like radians. All right, let's look at another example. So in this example, we're doing a much bigger section. We're doing a 240 angle. So let me rewrite the formula over here so we have it to look at. So if I put in 240 degrees over 360 degrees, then times pi, then times our radius, which is 5 feet, and we're going to square that. So always reduce your fraction first. So cancel out your degree marks, because the units cancel. I happen to have zeros again that will cancel. And then 24 over 36 reduces by 12, so that's 2/3. Then we have a pi. Then 5 feet quantity squared is going to be 25 feet squared. Now our idea is to multiply 2/3 times 25. So think of putting a 1 under the 25. And you have two options on multiplying fractions. You can multiply first and then reduce, or you can look at the diagonals to see if they reduce before you multiply. 2 and 1 will not reduce. 3 and 25 do not reduce. So therefore you get 50 over 3 pi feet squared, because you just multiply across the top and multiply across the bottom to multiply fractions. So it's not difficult to evaluate these problems. It's pretty simple. You just plug your numbers in and multiply everything together except the pi. Now, when I want decimal answers, we'll even multiply it all together with the pi. But sometimes you're asked to work these problems backwards. So in this problem, we're missing how many degrees. So I have no idea how many degrees goes over 360 degrees. But I know that pi is still in the formula, and the radius 3 inches is still going to get squared. But that's equal to 75 inches squared. And I move the a to the other side because you want your variable that is missing to always be on the left side when you're solving. Now this time I can't cancel anything in the fraction, so I'm going straight to doing the squaring first, which is going to make 9 inches squared. And then, well, I want to kind of change this problem up a little bit. I want that 9 inches squared to be over the 360, because you can put a 1 under the 9 and multiply those together. But the theta is not going to be with it. We're bringing the theta over here by itself because it's on top. It can come out of the fraction. And that's why I can put the 9 in, because he's on top. Because any top can move to the top of any fraction as long as they're multiplied together. You even could put the pi in the top if you'd like, because that might be helpful as well. So we're going to take this multiplying problem and get rid of multiplying. Now, most of the time people think the opposite of multiplying is dividing, and it is, but we don't know how to divide fractions. And so long ago we started trying to get y'all to understand to flip and multiply is how you get rid of fractions in multiplication. In solving equations, you've got to have tricks to work with. And this is one of the tricks, is to flip and multiply. That makes all of this cancel out. So now I can put a 1 under this 75 and look at what I can do with this. Well, first of all, inches squared will cancel out inches squared. So this time the inches squares cancel out instead of the degree mark. And that's because we're looking for an angle. The degree mark should still be there. Then the 9 will go into 360 40 times. And then we can go 40 times 50, 75. Or you could have multiplied the tops and the bottoms together and then went back and reduced. That's up to you. 2 carry a 2. 0 carry 0. No, that's not right. Zero carry a 2. Yeah, I got off a digit trying to do that in my head. But multiplying by 0 just adds a 0 to the end. So 4 times 75 comes out to be 300, and then I add that 0 back. So it's 300 over pi, because the pi is still on the bottom, and this is all degrees. And if I divide this out, this would make more sense probably, because if I divide 3.14 approximately into 3,000, that's going to be about 1,000 degrees. So this is actually spiraling around tremendously in this particular question. Let's look at one more problem with area of a sector in degrees. This time we have our angle. It's 90 degrees, so we're going to put it over 360. But we don't have our r. So we have no idea what r is, so we can't square it. And we're going to set it equal to 140 centimeters squared. So we can reduce our fraction again like we've been doing. 9 over that will come out to be 1/4. And you can merge that pi in with that by putting 1 under the pi and say pi over 4, which makes it look a little bit simpler looking than having the pi beside it. It also helps in your solving process because now everything is in front of r squared is in a fraction. So we can flip and multiply. And then we'll have r squared equals, because these pi's will cancel out on the diagonal and these 4's will cancel out on the diagonal. So now I can multiply 4 times 140 and get 560. Put it back over pi and centimeters squared. So last but not least, when you want to get rid of a square, you square root, because square and square root are inverse operations of each other. They cancel each other out. I do not know the square root of 560 or pi, so I'm going to leave that inside the square root. But I do know the square root of centimeters squared. It's just plain centimeters. And that would make sense if you think about it, because radius should be how long it is, and that's what centimeters is, not centimeters squared. That's how long and how wide. Alright, so that's the end of our area of a sector part for degrees. So let's now look at arc length in degrees. And first of all, in this problem, they've given us diameter because they've drawn the line all the way across and put the diameter in the center. So that's always important to notice. So radius is equal to 5 centimeters. Is important to know because you want all your formulas to be about radius in this class. We do not work with diameter. We always work with radius. Now let's talk about what does arc length represent. Arc length represents how long the line is from one end of the angle to the other, but actually on the circle. That's arc length. So it's a piece of circumference, because all the way around the circle is circumference. Now we know circumference has a formula of 2 pi r. Some of you may be familiar with pi d, but we don't use that formula because we want everything to be about radius. And so in this case, 2 pi r would be all the way around the circle. Well, if you want it to be arc length, and arc length, different books use different letters. Some use L or some use S. I'm not sure for why they use S, because S really doesn't have anything to do with arc length, but some books do use S. I personally like L for length, but it is equal to the number of degrees out of 360, that fractional part of your circumference formula. So at least these formulas are easy to remember because you already know half the formula if you know the circumference formula, and you just put this fractional part in front. So let's look at this example. So the arc length L is going to be equal to 60 degrees over 360 times 2 times pi times a radius of 5 centimeters. And again, please make sure you put your units in your question, because that way your units will already be on your answer when you get to the end. We cancel degrees, we cancel zeros, that reduces to 1/6. We can even multiply some of this together over here and get 10 pi centimeters, because that will shorten our question just a little bit. Next, we can put a 1 under the 10 and multiply this together and get 10 over 6, but 10 over 6 reduces to 5 over 3. The pi can stay on the top, or it can stay beside it, whichever one you prefer. And that's 5 pi over 3 centimeters. And again, we could change these to decimals if we wanted to. But right now we're trying to write exact. So arc length is just a little bit simpler than area of a sector because it doesn't have that square in there. Alright, and this one we have a really long arc because we're going all the way around this circle, 300 degrees. So it's almost the entire circle. So arc length again is going to be equal to 300 over 360 times 2 times pi times 2 centimeters. Alright, see if you can calculate that one yourself. I'm going to pause the video for just a minute, and you should pause the video and work this. Okay, so now that you have come back, and let's look at what you did and see if you did it like this. So first you're going to reduce by marking out your degree marks and marking out your zeros, and 30 over 60, 36 both reduces by 6, so that's 5 over 6. And over here, if you multiply that together, that's 4 pi times centimeters. You put that over 1, you have a choice here. You can multiply this together and get 20 over 6 and reduce, but that wasn't how I was taught in school. I was taught to reduce the diagonal, because 4 and 6 both reduce by 2, and if you reduce the numbers before you multiply, they're smaller and quicker and easier to reduce. The other diagonal doesn't reduce, so I multiply across the top and get 10 over 3. When I multiply across the bottom, pi centimeters. And you can put the pi on the top or write it beside. That doesn't really matter. That's up to you. But it's the same answer you get if you'd multiplied first and got 20 over 6, because 20 over 6 reduces to 10/3. So you decide whether you want to multiply first or you want to reduce first, because you're going to do both. But it's just an option of when do you do it. Alright, so now we're going to look at an example where it is worked backwards. So if I fill in the 135 degrees over 360 degrees and put my 2 pi r where I don't know what r is, so I can't fill in a number for it, then it'll be equal to 75 feet. And so I can still start with reducing my angle since I have it, but I can't cancel zeros this time because 135 over 360 does not reduce like that. There's not a 0 on the end, but they're both divisible by 5 since they end in a 5 and 0. In fact, I think they're both divisible by a little bit bigger number than that. But sometimes if your numbers get too large and you're not sure what it might reduce by, you can pick a small number like 5 and reduce it more than one time. Or you can put it in your calculator and math bracket and reduce it. So it reduces to 3/8, and you can just decide how much of that you want to do in your head and how much you want to do on the calculator, because sometimes these numbers, nothing may come to you right away on how to reduce it, but I knew it was reducible by 5. I wasn't sure about how much more, so I used a calculator to get that a little quicker for these notes. Now if I put a 1 under that 2 pi, I can see that 2 will go into both of these numbers on the diagonal. So this is 3 pi over 4 times r. And now I'll be able to flip multiply like we've done on many other questions. So we're going to flip multiply the 3 pi over 4 to make it 4 over 3 pi. And r is going to be equal to what we get from multiplying this together. But 3 goes into both of the numbers on the diagonal, because 3 goes into 75 25 times. So that makes 100 over pi in feet. And again, we could multiply that out and get a decimal if we wanted to. But right now I'm trying to work on exact answers, so I want you not to get the decimals quite yet. Alright, I think I'll skip over this, working this particular one backwards for the angle, because I want to get into radians and show you how radians work, and I don't want this to be too long a set of notes. So let's talk about radians. Well, first of all, there'll be a radian angle on your circle. That's how you'll know that it's radians. I don't see a degree mark, so that makes it radians. Now let's look at how do you change your degree formula into a radian formula, because that might help you to remember the formulas. If you forget one, you might could do this math to get your formula. See, 360 degrees is how far it is around a circle, but that's not the only thing on how far it is around a circle. It's also 2 pi all the way around, because that's how we label it when we're doing our drawing of our angles. So in that case, these pi's cancel out. Now this is 1 theta over 2, so you can separate those two things apart and say 1/2 times theta times r squared. And so I have taken a degree formula, plugged in the amount of radians that 360 is, and reduced it down to a new formula that is the area of a sector in radian formula. Now let's look at how you plug that in for this question. So A is going to be equal to 1/2 times the radian angle, which is 2 pi over 3, times the radius squared, which is 3 inches quantity squared. Now in this problem, you need to square this first, so this will be 9 and inches squared, because you got to square the unit and the number. Over here, these 2's will cancel, making pi over 3. Then when you put the last two pieces together, the 3 will cancel out the 9 3 times, because you can put a 1 under it, and you get 3 pi inches squared. So it's very simple to multiply these together. It's not really complicated, and the numbers are much, much smaller since we're working with radians instead of degrees, so they work out a little bit quicker. So in this problem, r is missing. Let's see how that works. So again, the formula is 1/2 theta r squared equals A. So it's 1/2 times the angle of 7 pi over 6 times the radius, which we don't know, so I wrote in r squared, is 100 centimeters squared. So first, this time, we want to put our 1/2 times our angle. Nothing reduces, so it's going to be 7 pi over 12. We've got to get rid of that fraction, so we're going to flip and multiply it. We're going to flip and multiply 12 over 7 pi to both sides. And that's going to give me r squared. Now that doesn't reduce, so that's 1200 over 7 pi centimeters squared. But we still aren't finished because we haven't found r. We found r squared. So we square root it. And r is going to be equal to the square root of 1200 over 7 pi times centimeters. I mean, not times centimeters, but the units is centimeters, because that's the only piece of that that's square rootable. 1200 is not a perfect square. 7 is not a perfect square. Pi is not a perfect square. So I just leave it in the radical for right now. So it's not difficult. In fact, the formulas are probably a little bit easier to work with. Not maybe as easy to remember, but easier to work with because your numbers are much, much smaller and easier to multiply and divide with. Now let's look at arc length and talk about the radian formula. Let's start with the one for degrees first and turn it into the radian formula. So we had our degree formula that was the circumference formula times the fraction. We can take out the 360 and put in 2 pi. What happens then is the 2 pi's cancel. So this is a very simple formula. It's just theta in radians times r. It's that simple. Oh, wait a minute. I wasn't paying attention. This is arc length. I'm supposed to be using L. But also some books use S, and in fact the assignment that you're going to have uses S, and I don't care for that because S has nothing to do with arc length. Don't know where they got that from. S sounds more like you're doing an area of a sector. So I like L better. So when I do L, I'm looking at just theta times R. So pi over 2 times 6 feet. The 2 will go into 6 3 times, so my answer is 3 pi. This is the easiest of the four formulas because you're just multiplying two things together and you're done. It's not real complicated to work with arc length in radians. It's just as easy to work it backwards. In this problem, we're looking at, we don't know what angle. We have no idea what the angle is, but we know the distance along the outside of this curve. Let me change colors. We know this distance right here is 48 centimeters, and we know that the radius is 6 inches. Excuse me, centimeters. 6 centimeters. So if I take the formula we just discussed about arc length being theta times r, then you will have, you're looking for theta, you have 6 centimeters to plug in for r, you have your 48 centimeters, and you can divide by 6 centimeters. Oh, it don't look like centimeters. 6 centimeters. And theta will be equal to, the centimeters cancel, giving you 8 when you divide. And you have to know to put the word radian back on it, because there's nothing in the problem to tell you to do that. That's one of the drawbacks to radians, is that if they don't tell you what unit they want it in, the angle has to be in radians. And so therefore, since it didn't say theta is equal to so many degrees, I know that the answer is in radians. So that's the end of our notes. You can go to Canvas now and find your homework assignment for 5.1 Part 2. It says to do 38 through 56 even, but pay attention because they are a little mixed up. They'll give you a problem with degrees and then maybe a couple with radians, and they do not use L. They use S for arc length and A for area. So you have to pay real close attention to them switching it up all the time between what they're looking for.